Hello and welcome to the podcast According to Sci-Faith, where we discuss topics revolving around the compatibility of science and faith. I'm Joshua Göcking and you're listening to According to Sci-Faith. Episode 18. Quantum gravitation, where is the problem? So, I several times already wanted to talk about quantum gravitation. It's not really my type of field. So if you know the German podcast, which you probably don't, but if you do, then you know that we talked about everything leading up to that point about quantum mechanics and general relativity. How can they be combined? But even if you don't know about this pretext, I think you can easily follow along with this introduction I want to give today. And in the next time, I just want to dive deeper into that topic, dive into the theories that come about now. Then we will also look into duality soon. And then I want to also look into theories like string theory and so on, and also look at the problems that these theories have or face, or why they are not confirmed yet or still considered to be not accepted or not widely accepted yet, and what the state of the research in these cases is. So, but if one wants to, so the question of course is, okay, quantum mechanics came about like in the 1920s. The theory of relativity even sooner. General relativity came about at 1915, and even the further theories, quantum field theory, was about in the 60s and 70s. It was formulated in its fullest. So why hasn't there happened something since then, or has there happened something? Why do we have not this complete theory of quantum gravitation yet? Why could we unite or quantize every other force than gravity? And of course, for one thing, gravity is much weaker than all the other forces, which is kind of funny because if you look into it, the first force you experience in life or every time is gravity. You experience it all the time. It keeps you in your chair. It was also the first force that was scientifically described, and the first force people were really aware of. And the next one was, of course, electromagnetism. And only later we became aware of the weak force and the strong force. But the interesting thing is that the direction in which we became aware of these forces is exactly the opposite to the strength of these forces. So gravity is the weakest force. Then there's the electromagnetic force, the weak and the strong forces. So actually, that's not completely true. The weak force is the electromagnetic force is stronger than the weak force, but not because of their coupling, but only because of that the weak force has heavy gauge bosons. But that's complete. If you don't understand anything of that, that's just a side note. So, but I think that's an interesting concept, that the weakest force was actually is actually experienced the most, and the strongest forces we do not really immediately recognize. Okay, actually you do, because the electromagnetic forces and strong forces and so on are also responsible for you not going through walls and so on. So you kind of experience them, but you experience them not as directly as you do gravity, for example. Okay, but that's only a side note. And so this is one thing why you might say, okay, that this could be on a subatomic level. Gravity plays no role. It cannot be measured there. So maybe that's why we cannot unite it with the other forces. But we want to look deeper in what a real problem is if we write out the equations and put in the physics that we know about quantum mechanics and general relativity, and why this becomes a problem. So what we need to first show is we need to have these things. Okay, what about quantum mechanics? What do we use? So first we have this Heisenberg uncertainty principle that we will use. And then we have this statement that in quantum mechanics, it's the case that everything that can happen will have a certain chance or probability of actually happening. And from relativity, we take this the statement that energy is mass. So, E equals mc squared. And many people get hung up on this c squared, but this is actually just a constant of proportional. So you can easily throw it out. So that's actually what theorists do. They say we choose our units such that the speed of light is equal to 1. And then this equation becomes pretty simple. E equals m. So this is saying that mass is a form of energy. And then we also use a statement of general relativity where it says you can make you can create black holes by putting a lot of stuff in a small place. So if we look into these statements, so first into the Heisenberg uncertainty principle, what does it really state? And what it does state is that you cannot simultaneously measure the momentum and the position of a particle to an arbitrary accuracy. So if I know that the momentum is basically the momentum the particle has, it's classically it's the mass and the velocity combined, and this is what basically its speed combined with its mass, and then the position of a particle. And if I know, for example, the momentum, then I really don't know where the particle is. If I know where the particle is, then I don't know its momentum, and there's this uncertainty in both these quantities. And there's another version in which you can formulate this. For example, you can equivalent to momentum and position, there is this uncertainty in energy and time, and from this you can state that it is possible to borrow free energy from empty space as long as you pay it back within a short period of time and nobody is watching. So this is basically if you have this uncertainty of energy and time, this means you have an uncertainty in energy and an uncertainty in time. And this also means that there can be no perfect vacuum, because there also needs to be some fluctuations in the energy, because otherwise you would know the energy perfectly well and would know that it is zero. But it cannot be. Therefore, there needs to be some fluctuations about the energy. And therefore, even in the most perfect vacuum, there will be particles popping up into existence and annihilating each other, which we call quantum fluctuations. And this is basically what I described before, that you can basically take energy from empty space, from nothing. Basically, you can borrow it, and if you don't keep it too long, therefore there comes the time aspect, then you can keep it, and then you can have to give it away again. So, by the way, just I'm following here in this the slides of somebody from King's College in London. His name is Eugene A. Lim. So his slides on this topic I'm following, and I will put these in the description also if you want to follow along. So now we look in quantum mechanics. So we just look at an electron traveling from left to right, and what then can happen is it can, as we have stated, it can borrow energy from the nothing, from the space basically, and emit a photon. It can let a photon go out, like radiating it from itself. Now, this energy, it has, of course, after some time, it has to give it back. So it has to reabsorb the photon, and after some time, and then everything is fine, energy is conserved, and we are in good physics again. So what then happens, you have kind of a loop. So the electron travels, it gives out the photon comes back to the electron and is absorbed. So you have kind of a loop there. And these are called quantum fluctuations, as I just said. And if you have seen sometimes the diagrams that are used in quantum field theory, you might have seen such loops of photons, of wiggly lines, and so on. And this is actually what's going on there. This is such a loop, and these are called virtual particles, and they are virtual in a sense that they are not real, in a sense that you can really measure them, but you can really measure their effect. So these loops, they lead to corrections to the amplitude that we calculate in quantum field theory, and there actually we need to include all possible energies, including even infinite energies, and this is done by adding up all these kinds of loops that can be created there, and summing this all up will give us this amplitude, our result. And so basically, if you ask what really happened, what really of these possibilities of particles being emitted and absorbed, or even two particles being emitted and absorbed, or one particle being emitted and it itself emits particles and is absorbed, and so on, what of this is happening? And the answer is all of them at once, and in some kind of way, and the probability of any process is the sum over all these possibilities. This is, if you remember the path integral formalism that we in a previous episode already discussed, this is basically what's behind it. It's basically the path integral formalism in quantum field theory, that all these amplitudes need to be summed up together and build the whole probability of this process occurring. And if one sums it up, and there are certain possibilities what can occur. So the first possibility is that we will get a finite number. And if this is the case, then that's wonderful, because then our theory is complete, and then we can continue. Another possibility is, of course, that we get a number which is infinity, if infinite in its size. So this number does not converge to some value, but it gets infinitely huge. Then we have a problem, because infinite numbers in physics do not make any sense. That's we cannot use that, because it's not predictive. We cannot predict anything from an infinite number. When we have this, when you have infinity, we know something in our theory is not working. Our theory is not predictive. And what we know then is that our theory might be incomplete, so there might be a problem with it. And this can be seen by a radioactive decay. We have beta radiation, where an electron is emitted. So basically what occurs there is a neutron decays into a proton and an electron. And since this, I don't know if we discussed it in the English podcast, but this is not if one particle decays in two particles, the energy spectrum of this would be discrete. But the energy spectrum of the radioactive decay is continuous. Therefore, you need a third particle in this process, which is called a neutrino, which basically takes care of energy conservation. Okay, it's time for a short break. Maybe you have heard of it, but recently Elon Musk told about his new research of his company Neuralink about human brain machine interfaces, where you basically with your brain you can access a computer or a smartphone or some apps and so on, and where they were showing first results of these experiments that they did. What I think is really interesting about this is that my book that you can order now also in English, Alien Thoughts, is really about exactly that topic, about some neurochip that is implanted in the heads of people, and with which they can do similar things, and also with some side effects that occur in those. So what is even more funnier than this, I wrote my book, the most part of my book was really finished before I even know about Elon Musk's company and about what they were doing, and even knew about the name of this. And in the end, if you have read my book, you notice in the end there is some, I think I call it neural connection there, that they have there, and this is something that they use the neural chip for, with which they can do some stuff. So read it if you want to know more about it. But the interesting thing is, in the beginning, I planned to call this a neural link, and only when I found out that they were really working on such things and that the company that is working on it is actually called Neuralink, I decided to change the name a little bit to don't make this association to this company. But I really think it's interesting that something that I really had in my mind, only I was thinking about it, and some not so distant future it might come. The future of this is not even as distant as I thought it would be. It's even closer in some degrees. I hope not the future that is described in this book, but still I think it shows that it's a pretty current theme, pretty current also in the technologies that are described there. So if you're really interested in scientific topics or sci-fi topics, then I really encourage you to read it. And also, it's not a pure science fiction novel. It's also a lot of spies and of adventurous stuff is in there. So if you enjoy these kinds of novels, then I really encourage you to read it. And I would really like if you would order the book. And of course, if you have already ordered it and read it and you liked it, then I would really encourage you to write a review, such that other people will know what the book is about and can see if this book is something for them. If you have this process that we look into, so a neutron and a neutrino decaying into a proton and an electron, so we have this process, and we want to look into the quantum fluctuations, if we can make it work there. And as it turns out, if we do this, we will receive an infinite result. So this is one example where this theory we have does not work. So what do we do now? Do we need to avoid this theory? Do we need a new theory? What can we do? But I mean, as we have seen, without the quantum fluctuations, we describe the physics, right? So everything is fine unless we include these quantum fluctuations. So that in a certain limit, something needs to go wrong. So maybe it's not completely wrong, but only incomplete. The theory is incomplete. There's something happening that we are not keeping track of. So let's try to fix this theory. Instead of throwing it away, let's try to fix it. So again, we consider an electron that emits such a virtual photon that it reabsorbs. But now we're changing something up. Now we say there's another electron, and instead of the photon being absorbed by the same electron that also emitted it, this time it is absorbed by this other electron. So one electron emits a virtual photon, and this is absorbed by the second electron. So if you, as a side note, this is actually how forces do work. So on a subatomic level, forces work in such a way that if two electrons are coming closer to each other, I mean, we know they repel each other because they have different charges. And the way this works is that one electron will emit a photon, which will the other a virtual photon, which the other electron will absorb, and this way they know, oh, okay, there's somebody coming against me, and they will repel each other. This is how forces works, and therefore the photon is not only a light particle but also the force mediator for the electric force. But it's only a side note. So we now have this process where one electron emits a photon and another electron absorbs this virtual photon. So it absorbs this photon where the energy of it was basically borrowed from space. And now we assume that in our Fermi theory, which it is called this theory of radioactive decay, something similar happens. So instead of a neutron and a neutrino decaying into a proton and an electron, we have a neutron and a neutrino who exchange some new virtual particle we call W, and out of this exchange they decay into a proton and an electron. And yet now we know from special relativity that energy is mass, and so from this we can use the energy that would be needed for this particle W. We can use it to say that's the mass of this particle. So or the mass of this particle can be produced by the energy we borrow from space. Basically, this virtual particle can come into virtual existence, so to speak. And if we postulate this, then we find that we need also the existence of several more particles, like a Z and an H. H is for Higgs. And if we recalculate everything, then we see that these infinities disappear, and our theory is now complete. But for this, we need very massive particles. So the W, the Z, and the H particle need to be very massive. The Higgs particle, for example, so the H particle is 125 protons heavy, and the W boson is about 90 protons heavy, and the Z 80, or I think it's the other way around. But so they are very, very heavy, which is, as I mentioned before, the reason why because this is the weak interaction, is actually weak. It's actually weaker than the electromagnetic one, although it actually would be stronger in its coupling. But that is, again, a side note. So now these particles could also be observed at a Large Hadron Collider in CERN, or the Z and the W were observed in a synchrotron particle collider, also at CERN in 1983. The Higgs was discovered in 2012 at CERN, at the Large Hadron Collider. And with this complete theory, this is now the complete theory of electroweak interactions, and it has been highly successful and predictive. So the principle we used here is we had some theory, then we checked this theory if it gives finite results. If it makes finite results, then we check it in experiments if it's correct. If it's correct, great, we are finished, Nobel Prize coming. And if it's wrong, then we have to find a new theory. But if we have infinite results, then what we do is we do not give up there immediately, but we add particles with a big mass to this theory until the theory yields only finite results, and then we check it with the experiment, and if it works, great. If it doesn't work, okay, then we really have to find a new theory. And so now let's look into general relativity. Let's look into how we can deal with that. So in general relativity, as we know, this is the theory of gravitation. And so we have to find something to describe gravitation with. So in gravitation, as it was discovered in recent years, there are these gravitational waves which long have been assumed to exist, or which completely also follow out of general relativity. And those would, on a subatomic level, they would be a particle, and this particle would we call a graviton. Which has not been observed yet, of course, but it's some particle that's going, for example, in the same sense as we described before. We imagine this graviton is going from left to right. And again, we will there have these loop corrections. We will have the particle emitting some other particle, maybe even another graviton, and absorbing it again, and so on. And then we check with all these loop contributions what kind of results we will get. And as it turns out, we will get infinite results. So we will get contributions that are infinitely big. And therefore, general relativity obviously only works if we ignore quantum fluctuation, so no quantum gravitation there. So maybe our theory, as we assumed before, is incomplete and we can fix it somehow. So let's try to fix it. And what we do is, again, we assume two gravitons, and now they exchange this particle, this virtual particle, which we call P. So we have this hypothetical virtual particle, and we want this to come in there, and now we want to compute as before which energy would be needed for such a virtual particle to come into existence and lead to finite results. And what we find is that this particle needs to be really, really, really heavy. So on the slide, he has there a number of 1 with, I think it's 18 zeros, and then this times the mass of the proton. So it is a really, really heavy particle. But for now, we say, okay, so the particle has to be heavy. What's the big issue with it? But now there is the statement from general relativity coming in that says if we put a lot of mass in a small area, this space will curve so much that it becomes a black hole. And actually, the mass of this virtual particle we defined here would come in this area where it is so heavy that there would a black hole be created. And what's the problem with a black hole is that a black hole is also called a singularity, and this is also a version of infinity. So with this new particle, we get a black hole and infinities, and the black holes exist, but their existence makes our quantum theory non-predictive. So we win nothing with it, and our theory will not be predictive in any way. So this is the real problem. So why is it hard to unify quantum mechanics and general relativity? So for one, because quantum mechanics says that you can borrow so much free energy from empty space that the general relativity would then say that you make a black hole. And if you now ask, but black holes exist, as we do know from observations in space, so what's the problem with it? But the existence of these black holes make this quantum theory non-predictive because we have singularities and infinities, and there's just no way to make proper predictions from those. And therefore, that's the reason why it is so difficult to find a theory of quantum gravitation. So that's everything for today's episode. I hope you liked it and you enjoyed each part of it. If you want to get in touch with me or discuss a topic or want to give me some feedback, then feel free to contact me using the contact form on my website, sci-faith.de/en. And there you can go to the contact tab and contact me. And if you have any other things or episodes you want to have covered there, or topics you want to have covered, feel free to contact me there. Also, if you are not yet familiar with the format in which this podcast is produced, let me just briefly explain it to you. So there is always at the beginning of a month or of a block, there is a big block of 4 episodes in one thing. It's kind of like a preview, which I call it, where you have the next 4 episodes all in one episode together, combined. And this is for people who like to hear long format podcasts, who have a long way to work or something else, where they can listen to a long episode and can then have a preview of the next 4 episodes all at once, and are completely up to date from the beginning of the block. For those who like their episodes shorter, who prefer it if they have a half an hour or even less of a podcast episode, for those there is every week afterwards will appear a podcast episode almost in that length, and this way I can publish every week a new podcast every episode, and everyone can have it his own way, either once a month a long chunk of content, or once a week a shorter format podcast episode. So I think that's the best way for everyone, and also for me when I'm producing it. Please also note that this is an independent podcast, which means that it is recorded, produced, and marketed by me. So I really need your support in this. So if you like this podcast, then give it a 5-star rating. And if you have the time, even write a review to it. This just helps other listeners to become aware of this podcast, and then people who might be interested in this content can become aware of it. Also, if you have friends who you think would like this content, then recommend it to them and share it with them. Also, you can support me in other ways, for example by reading my blog and subscribing to my newsletter, or even by reading my books, which you can find on Amazon. For example, there is my latest novel out now is Alien Thoughts, which is pretty entertaining from the feedback that I gotten, and so it's also in some way related to science and faith. The topic of it is also in there, but of course you can also read the book to this podcast, Sci-Faith, The Compatibility of Science and Faith, which is also available in English since last year. Thank you for that, and now I wish you a wonderful day, and I'm looking forward for you to tune in again next time.